Okay, so let's go to simulation part. So let me click initialize and go to the scenery, select scalar view, use S to go to side view, and in the function bar right click and select volume fraction. Let me drag this bar upward so we can see the selection. So let's go to volume fraction of water, right? And then we would like to also create a cross section of this uh, simulation domain. So go to section plane. So let's make the plane normal to Y. Then in existing displayer, we like to show this plane in scalar 1, create, close. So you can see so far volume fraction of water is 0 everywhere because it is filled with air, and in the boundaries of the water inlet we already set up the volume fraction, but we didn't set up the velocity. By default it is 1 meter per second, normal to the surface, so it will inject from this corner and inside this fluid domain. So let's see what happened when we start our simulation. Right, so this is the residual view. Let's go to scenery plane. So you can see the water is coming out from this corner. This simulation might take a while to reach steady state. Alright, so the simulation is take for a while, and we could see this is current result of the two-phase fluid flow. We could see the water has parabolic trajectory from the left top corner going to the ground of this simulation domain, and we could see this is parabolic trajectory from Excel. So if the water is entered at 1 meter per second and only governed by gravity, then that's the trajectory, and it will land it roughly about 45 meter at the bottom. We can see this is quite similar. So that's we could say this simulation has certain realistic physics which govern the water motion in the computational domain. And also, if you don't like this color here, you could change the color map in tool. So we could go to color map and create a new color map. I think if we would like to if we could apply high pass and low pass color map, maybe this is better described the two-phase flow. Let's just go back the scalar color map at current stage, and let's see, use blue rate, high pass. That's probably not good. Okay, so maybe let's use this one, blue rate, low pass, and use a reverse function here, so we could only see the water here. The space resolution is 1 centimeter, which might not be good for our simulation. You can see those space resolution is too coarse, so it become less easy to see the detail of the two-phase flow, like breakup phenomena and splash, so on and so forth. So if you would like to see those phenomena, you need to make sure the mesh is fine enough, and you could go back to the mesh model and reset the reference value of the base size, then uh, click the mesh button again, then you will get a new mesh. And the next thing is the Cfl number, or Louis Friedrich Kuhlmann Friedrich Louis number. The number is defined by U times time resolution over space resolution of the simulation. If the Cfl number is greater than 2, then generally speaking, the simulation is unstable. So we could check out the Cfl number in our simulation case. So Cfl number is equal to roughly the maximum velocity is around 5 meters per second at the bottom. So we use the maximum velocity in our simulation case, which is 5 meters per second, times the dt is 1 microsecond over the space resolution is 1 centimeter. Then we have the Cfl number equals to 0.5, which means we are good here because this number is less than stable criteria. So let's check. You could also check the Cfl number right here. Let's just open a new scalar view right here, and go to scalar. In the part, we need to select the rift part, which is the plane we just created. Select the function of, okay, let me drag this bar upward and right click. Select convective Coulomb number. This is another way to describe Cfl number. Let's see the maximum number right here reaches almost 1. Maybe we could check the velocity here. The velocity is velocity, vorticity, velocity right here, magnitude. Yes, so the velocity at this corner is the highest point, which is 9.2, which is more than what I expected because I only calculate the theoretical velocity at the bottom right here, but there's a lot of momentum conservation and mass conservation at the bottom, so some small part of liquid being squeezed and accelerate to different directions, so they might have much higher velocity than at the bottom here. So that is one reason why they have much higher velocity than theoretical predicted. But we could go back to Coulomb-Friedrich Louis number or convective Coulomb number right here. So which is 0.9. That means this simulation we have some confident level that this simulation is simulate the right thing. We could change the dt here to make a comparison. Before we do that, maybe let's add a annotation here. What I would like to do is add solution time information, so we could know what is the time right now here. So the time is roughly about 0.5 seconds. So that's export this figure, export it to desktop. Make sure the resolution is the same for different figure. Okay, so I pretty much just use the default setting. Let me save this file. Save to desktop. New folder called 2 face. Oops. two-phase flow. Okay, so inside two-phase flow, this is start 1 millisecond. Let's see what happens if we increase the dt. So let me go to the setup, implicit unsteady. Let's increase the interval of the time resolution, and we go to solution here, clear solution. So we would like to clear off the information inside and rerun our simulation. So we are done on the 10 millisecond DT simulation here. So we could check our simulation result. So this is the volume fraction of water based on 10 millisecond DT. The Cfl number for this case is about 10, so which means the fluid information is unstable, because based on that speed of fluid, it passes several different space resolution in one single delta t, and which create uncertainty in simulation. So that's why it becomes less trustable if we have Coulomb-Frege number is much greater than 2. So you can see this is the result of 10 millisecond DT setup. We could see the image right here, comparison, which will be easier. So this is 10 millisecond simulation result of water trajectory. This is 1 millisecond. So based on the same setup, the only difference is the DT setup, and we could see there's a lot of difference between correct time setup. So in two-phase flow, the Cfl number will be one important reference value for simulation, and the realistic of the simulation should be checked for Cfl number inside simulation domain. Alright, so I think we just finish everything here. So maybe let me stop right here and use a quick demo in the next video to talk about how to create a 3D view in scenery setup.